An easy way to deduce hybridizations is to count groups around a central atom. A group is defined as another atom or a lone pair. When an atom is surrounded by 4, 3, or 2 groups, it will adopt the sp3, sp2, or sp hybridizations, respectively. A helpful way to remember this is by adding the exponents together. That should equal the number of groups around the hybridized atom. For sp3, the exponents add to 4. Thus, an sp3 atom has 4 groups. For sp2, the exponents add to 3. Thus, an sp2 hybridized atom has 3 groups around it. These hybridizations allow the respective number of groups to be as far apart as possible. Again, think of it as all groups attempting to minimize electron repulsion. Although we will use the abbreviated hybridized building block shown here for subsequent examples, it is important to recall the actual shape of the unhybridized and hybridized lobes on carbon. For example, the unhybridized lobes were shrunk to 1/3 of their size, and we simply showed how the electrons in the hybrid orbitals were oriented in 3 dimensions, so that the carbon building block does not become too cumbersome and confusing. A simple carbon compound that utilizes both sp3 and sp2 carbons is propylene. From the 2-dimensional Lewis diagram, we see that by counting groups, we can deduce the hybridization for each carbon atom. 4 groups employ the sp3 hybridized building block, and 3 groups employ the sp2 hybridized building block. Starting with 1 sp3 and 2 sp2 hybridized building blocks, we can start to build the molecule in 3 dimensions by forming the carbon-carbon sigma framework. Next, the 6 carbon-hydrogen sigma bonds are formed, followed by the pi bond, affording the final 3-dimensional molecule. Notice that the methyl group can freely rotate about the carbon-carbon sigma bond, while the pi bond affords no rotation. Within acetamide are central atoms that we have not dealt with yet, nitrogen and oxygen. However, we employ the same concept for deducing hybridization. Simply count groups on these atoms, which means we also have to count the lone pairs as groups. 4 groups around nitrogen and 4 groups around carbon allows us to deduce sp3 hybridization, while 3 groups around the oxygen and carbonyl carbon allows us to employ sp2 hybridized building blocks. Once all the hybrid building blocks have been deduced, we assemble the sigma bond framework, attach the hydrogen atoms, and form the double bonds as shown. Again, we see that the CH3 group can spin freely about the carbon-carbon sigma bond, while the pi bond affords no rotation. In addition, the NH2 group can spin freely about the carbon-nitrogen sigma bond. Now let's look at a compound that utilizes an sp hybrid building block, carbon dioxide. Again, from the 2-dimensional Lewis diagram, we see that by counting groups, we can deduce the hybridization for each atom. 2 groups employ the sp hybridized building block, and 3 groups employ the sp2 hybridized building block for both oxygen atoms. Starting with 1 sp and sp2 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming both CO sigma bonds. For both pi bonds to form, we need to rotate the oxygen on the right forward so that the adjacent unhybridized 2p orbitals are parallel. Thus, both pi bonds form, affording the final 3-dimensional molecule. Notice that the two pi bonds are perpendicular to each other. In addition, the lone pairs on each oxygen atom are perpendicular to each other. As you become comfortable with the concepts of hybridization, you will be able to fold two-dimensional Lewis structures into 3 dimensions in your mind. With practice, you will also be able to allow the molecule to undergo conformational changes in your mind while predicting the more stable conformer due to steric interactions and other effects. Here we see that the methyl group prefers to be in the equatorial position. Thus, one of the chair conformations is favored over the other. As we have seen, ideal bond angles are obtained from the hybrid building blocks. However, deviations from ideal bond angles can and do occur in virtually all molecules when groups are not equivalent. For example, the sp3 hybridized oxygen of water has a lone pair interaction, which will cause the two hydrogens to become closer than their ideal bond angle of 109.5 degrees, about 104 degrees. VSEPR, valence shell electron pair repulsion theory, allows the chemist to make predictions regarding deviations from ideal bond angles. A general trend that allows predictions from ideal bond angles is lone pair interactions are greater than lone pair bonding pair interactions, which are greater than bonding pair interactions. The sp3 hybridized nitrogen within the ammonia molecule has 3 lone pair bonding pair interactions, which will cause the 3 hydrogen atoms to become closer than their ideal bond angle of 109.5 degrees, about 106 degrees. An interesting property of nitrogen is that it has the ability to undergo inversion of configuration, demonstrating that hybridizations can transform. For this umbrella-like effect to happen, we see that the nitrogen hybridization appears to change from sp3 to an sp2-like nitrogen, and back to sp3. Current theories predict that there are 200 billion inversions per second for a molecule of ammonia.